Hello everyone. In this lecture, we will be studying about operating system operations like hardware protection and system calls provided by the operating system. As I mentioned earlier, operating systems are interrupt driven, and I told about two types of interrupt, that is hardware generated interrupt and software generated interrupt. In hardware generated interrupt, many errors detected by the hardware can be handled by the operating system. Software error handled by exception or trap. A trap is a software-generated interrupt caused either by an error or by a specific request from a user program that an operating system service need to be performed. For each type of interrupt, separate segments of code in the operating system determine what action should be taken. Since the operating system and the users share the hardware and software resources of the computer system, we need to make sure that an error in a user program could cause problems only for the one program running. With sharing many processes could be adversely affected by a bug in one program. For example, if a processor gets stuck in an infinite loop, this loop could prevent the correct operation of many other processes. We know more secret or thin errors can occur in a multi-programming system, where one incorrect program might modify another program or even the operating system itself. So without protection against these sort of errors, either the computer must execute only one process at a time or all output must be suspect. A properly designed operating system must ensure that an incorrect program cannot cause other programs to execute incorrectly. In order to ensure the proper execution of operating system, we must be able to distinguish between the execution of the operating system code and user-defined code. The approach taken by most computer systems is to provide hardware support that allow us to differentiate among various modes of execution, which we call dual mode operation, allow operating system to protect itself and other system component. Now, to important modes of operation, we need to know in which a program can execute, which are known as the user mode and kernel mode. So let's try to understand what is this user mode and kernel mode. If a program is executing user mode, then the program does not have direct access to the memory, to the hardware and such resources. But if a program is executing in kernel mode, that program have direct access to the memory and hardware and such resources. So we can say that if a program is executing in kernel mode, then it is in a privileged mode because it is having direct access to many resources. User mode is a safer mode of operation and kernel mode is a privileged mode of operation. Though the user mode is safe, most of the programs that execute mostly in user mode, but when a program is executing in user mode, it may need access to some of the resources like memory or hardware or so on. So when the program needs access to the resources, to those resources, it makes a call to the operating system telling that I need access to certain resources. So it makes call, and for instant user program switches from a user mode to kernel mode so that it can use those resources. And then the call I am talking about, the call that the program makes in order to access those resources or to go into kernel mode, that call is known as system call, which I discuss further in this lecture. Mode bit is used here to distinguish between user and kernel mode. We can see here that user mode is represented by mode bit 1 and kernel mode is represented by mode bit 0. With the mode bit, we can distinguish between a task that is executed on behalf of the operating system, that is 0, and 1 is executing on behalf of the user. When the computer system is executing on behalf of a user application, the system is in user mode. However, when a user application requests a service from the operating system via a system call, the system must transition from user to kernel mode to fulfill the request. This is shown in this figure. We can see here uh, upper this line, this is the user process, and below the line, this is the kernel of the operating system, and a user process is executing here, which maybe needs some resources of the system, and it makes a system call. Whenever it makes a system call, okay, it change its mode bit from 1 to 0. And when the mode bit is 0, in that mode, it executes the system call and return to the user mode again, or resume to the user mode again by changing its mode bit to 1. Now come to the next topic, that is system call. Here we will try to understand that what is system call and what are they used for. System calls provide an interface to the services made available by an operating system. Or we can say that a system call is a way for programs to interact with the operating system. A computer program makes a system call when it makes a request to the operating system's kernel. System call provides the services to the operating system to the user programs via application program interface. So when the program makes a call to the operating system saying that I need to use some particular system resources, then the context switch happens when the user mode is switches to the kernel mode, so that the program can use those resources. And the call, that what we are talking about, is the system call. So we see that system calls are made by the program when it needs to access certain resources. So when a program executing in user mode needs to be switched to kernel mode for a particular time, this system call is made. So in this way, we can understand system calls, or we can say that system call is a programmatic way in which a computer program requests a service for the kernel of the operating system. These calls are generally available as routines written in C and C++. Each operating system has its own name or each system call. Let's see an example how system calls are made or used. Let's see, we can see here in this figure where we want to copy the content of one file to another file. So here we can see some system call sequence for copying data from one file to another file. So here we have source file which we need to copy to destination file. In order to copy the content from source to destination file, we need to get the name of input file. So we need a system call in order to acquire the input file name. And then write prompt to the screen means asking the user to enter the name of the input file. For this also another system call needed. And for accept input file name, another system call also needed. So here all the lines, they represent individual system calls. After that the next three system call are made here. Get the output file name same as the input file name. Then we can start copying input file. That we need a system call that is open the input file. If the file doesn't exist, then abort. For that purpose, another system call also be needed. Then you have to create a new destination file which do not exist. If exist, then it should be aborted. So for this purpose, another two system calls is going to be needed. Till now, if everything is okay, then next we need a loop for copying content of input file to another input file to output file. This loop runs until the read fails, means there is nothing left to read. We need a loop of system call over here. And after everything is copied from input to output file, we need to close it. Means another system call is needed. And the message will display on screen for displaying copying process is completed. So for this purpose also we need another system call. And for lastly, terminating the entire process, another system call also needed. As you can see here, even simple programs may make heavy use of the operating system. Frequently, systems execute thousands of system calls per second. We should remember that system calls are always being executed in our system. I hope that I make you all understand about system call. Typically, a number associated with each system call. System call interface maintains a table indexed according to these numbers. The system call interface invokes the intent system call in operating system kernel and returns status of the system call and the return values. The caller need know nothing about how the system call is implemented. Here, the relationship between an API, the system call interface, and the operating system shown in this figure, where the handling of a user application invoking the open system call. Thank you for listening, everyone.